In the first lecture, I have described the nature of the course content and the distribution marks for quiz 1, presentation, seminar and internal exam, and the reference books and the method of grading. And I have described some per capita consumptions and the generation capacity of the world and our country, and we have tried to correlate them, how you can come back from generation capacity to per capita or per capita to generation capacity. By this method you can calculate. Okay, it's very interesting calculation, so please go through it. I will upload these PowerPoint slides. It's a very important concept. Then we also have discussed that different countries, how we stand in the whole world. Normally when we start the course, we start talking about the concepts. I will talk about them, but I want to make you feel that how the world is and what are the total generation capacity of the world, country, where do we stand, what we need to do in the coming time, where we should focus as a nation, as an engineer, as a academicians, and all those factors, so that you have a broad view of the things around you before you jump into the course. It is important to really understand that what is the big scene in the world in terms of the renewable energy and in terms of the conventional energy. So I hope this presentation will give you open the broad area of understanding in terms of the energy and its production, its uses, and its future scope of requirement, that where we need to focus. So I was telling you that in previous slides presentations that if you compare the India's population and India's geography, then we are lagging almost 4 times than what we should be at the world average. As I said, the India population wise is close to China, but area wise it is 1/3 of China. This point if you look, okay, 3 times less than China and USA. USA and China have almost same area, close to same geographical area, but USA has population 1/4 times than us. So, and 3 times bigger than us by geography area. So USA get direct advantage of 12. 4 into 3 is 12 times. So even they won't do anything. Even they are far better position than us, because we have a more population, we have a less area. So that is a drawback that our country has, and the drawback can be only overcome by having a very great expertise for each and every person in our country. That can only be the hope, because we have a large number of people. Okay, so our human resources are very high. That's a good point one way, but if they are not skilled, if they are not aware of their responsibilities, if they are not aware of their country, then it is a disadvantage. We will talk about this briefly. So you can see here that India is 3 times less than China, but its population is almost same as China. So we have a 1/3 disadvantage of the China, and we have a 1/12 disadvantage of the USA. Now you can see here, this is graph you can go through when you have time, but what I am telling is that if we compare the per capita electricity consumption over top 20 countries, we are not coming in top 20 countries, and Iceland is the one which is having the highest per capita consumption of electricity. Then comes the Liechtenstein, then Norway, Kuwait, all those, and there is Australia, United States at 10th rank, Canada at 7th rank, and China stands at 69th rank, and we stand at 153rd rank. So this is the third quarter, you can say, or the last quarter, and China stands at the third in the beginning quarter. So we are still at a disadvantage in terms of the electricity generation and its uses. If you look, a very interesting study that is called per capita electricity consumption into population density. What is that? If you multiply per capita electricity consumption or electricity into population density, what will you get? We will get how much electricity is consumed for pupil over per square kilometer. I was curious to know, this figure you will not find anywhere. Just I have thought about this and I tried to see that what about the electricity consumption of the countries in the world over 1 square kilometer. So this adds the additional feature of population density, per capita consumption into number of people over per square kilometer. A very interesting feature we found. What is that? If we do that, then we find that the where is that number? Here. World. You see that this number 0. The 0 I have called as the world. Do you see this column? 99?
Yes, sir.
99 is almost in the middle. If we have almost how many countries we have? Close to 218, you can say. So 218 is the number of countries, including smaller countries, even including Vatican City and all those, Macau, all those things. So if you come to 99th number, then you will see this is called world average. So I have a world population. This is the world geographical area. This is the world population, 7.57 billion. And then what is this number? This number is population density. So world population density is, I will come the average point first, 56. Okay, so 56 people per square kilometer. Am I correct? Sorry, world population density is where? E is the population density. So this is the population density. It means there are 56 people per square kilometer in the world. This particular cell, 56 people per square kilometer. Now, if I multiply this 56, okay, with the per capita, this is the per capita consumption. What is the world per capita electricity consumption? 3036. What is India's? Around 1000. We are 1/3 of the average of the world in terms of the electricity consumption. So if we multiply this figure with this into this, okay, the number of people per square kilometer into the per person electricity consumption, this is a 17.17 million, or you can say 1.7 lakhs of the electricity consumption over 1 square kilometer. Let us call this number as a 1. Let us call this number as a unity. Reference parameter, world average is a reference. So I will divide all numbers with this number for other countries. So if you start with this and come back to the top, then Macau is the highest kilowatt power usage for 1 square kilometer, because the generation is very high and population density is very high, 7,532. Okay, this is the average, and population density, you know how much? 21,230. It's a small city actually of China, Macau. Macau University is very famous. So this is a very highly densely populated city, but they call it separate land, separate country. Otherwise it is a part of China. This is 940. The final number is index is 940. This be found out ourselves. You will not find the study anywhere. I just thought about this figure of merit and I plotted in terms of the table. So the study you will not find. So this is 940. Now coming to other countries, South Korea is 29.3 figure of merit. Then Japan is 14. Okay, one is the world average. You go on like this. Germany is 9.0. United Kingdom is 7.6. Then Italy is 5.54. France is 4.6. And then China is 3.6. As I said, China stands more than average of the world, so it is 3.6. It goes like this. India is 2.6. Not bad, because we have a high population density. We have a less per capita, but we have a high population density, because that the number is close to China. And if you see USA, it is around 2.34. So if you look that way, we are better than USA. Why it is better? Because we have a more population density, but we have a less electricity consumption per person. But to multiply these two numbers, then we will find 2.65. It actually means that if the USA would have been as smaller as us, and its population would have been as big as we have, then we will be at the same platform. Okay, this is a rough way to understand. It's not always true, because how people are efficient, how they are hardworking, also depends upon that. But I am taking the concept that on an average people are equivalent efficient. Okay, more or less same efficiency is there. Then this comparison holds true. Now if you come further down, very interesting point is South Africa is 1.05, which is close to world average. So that way we are better than world average, because our density is very high. And if you come to the Iceland, which is having the highest per capita consumption, is below the world average. Why? Because there are very few people per square kilometer. So the electricity consumed there in per square kilometer is very less. All right. And this goes to Russia, which is 0.39. Why it is so? Because again population density is very less. And then come to Brazil. Okay. And finally we'll come to the other countries like Greenland, all those things, very 0.0009. So this study shows that the geographical area, the population density, and electricity generation, these are connected parameters. But if you look in terms of the consumption per person, then we do not stand well. But if you look at our population, it looks okay on average, we are okay. But we need to work a lot to come to even the world level in terms of the total generation per person. So I hope you understand this concept. Then going further in terms of the energy, as you see from this graph, that China, United States, India, and then European Union, Southeast Asia, Middle East and Africa, if you look. So the red color shows the growth at 2040, and the blue color shows, or dark gray shows, the 2016 currently. So what we see, that China has almost 40% potential for growth. United States maybe 10%. India has more potential to grow over the next let us say 10 years or 20 years. You can see it here. The red color region is more. European Union have very less scope to grow because they are almost saturated. Similarly, Southeast Asia and Middle East and Africa have a more potential to grow. So we still have a more scope to expand, to develop our future of energy technology, energy reservoir, to supply electricity to everyone. And now we come to renewables. Now we will ask the question, well, okay, you have almost close to 6,000, 7,000 gigawatt hour world generation, and 326 is for India's share, which is 5%. But how much is the total percentage of generation as renewable energy? So this graph will show you, this is a little old, but more or less they have the same variations, that the renewables totally is around 19%, maybe now 25%, 20%. So it is almost close to 1/5 to 1/4. Okay, the rest of the fuel sources or resources are still petroleum, this side, the coal and natural gas. This total forms around 78.4. You can say approximately 75%, three-fourths of that, and 1/4 forms renewables. So renewables is still not, and in this renewal also we have a huge contribution by the hydropower, which is 3.8%. You can look here, this column, okay, this row. Hydropower is 3.8%, and bioheat is almost 2.6%. They are largest. Traditional biomass is 9%. This total makes 19%. Okay, this is the percentage of 19 actually, or you can say the 9% of the total. It's not the 100% of the renewable energy. So this forms the total percentage. Okay, so you see here the wind power, the solar PV is 0.07, not much, and concentrated solar panels is 0.0039, and you see ocean power is 0.00, very less. Wind is 0.39% only, which we talk mostly, wind and solar. They are very less as compared to the hydropower and the bioheat and the traditional biomass. Okay, and particularly the ocean power is, we expect more to develop, but it is very less because the mechanism of trapping the energy from ocean is very difficult, although it's abundant. Going further on these lines, and we see that what is the global overview, then we say due to the major concern of the temperature rise and the CO2 effect, environmental problems, the renewable energy has got a more attention and it has gained the huge impetus. Also, the renewable energy, mostly consisting of hydro plant, wind, solar, etc., has doubled over the last decade. So definitely there is a significant progress, but still it does not contribute significant of the total generation. If you look 2017 data, then we found around, say, some change from 19 to 26.5% change in 2-3 years back, you can say almost close to 4 years back. So 73.5 forms the non-renewable or fossil fuel, and then 26.5 forms the renewables. Out of that, 16.4 is basically hydropower. 16.4 is hydropower. Where is that? Okay, and out of the 16.4 hydropower, the remaining is, how much is this? Remaining are 5.56% wind, 2.2% biopower, 1.9 solar PV, 0.4% ocean, other things. Total makes 26.5%. All right, clear? Okay. Now coming to the solar potential, although you see from the previous slide that the contribution of solar is very less, but it is expected that there is a huge scope for the solar potential. There is a huge scope to tap the energy from the solar. Although we have no idea that whether it will be okay for us in terms of the ecology, environment, other things. People say it is harmless energy. I mean, we can tap infinite energy, almost abundant energy, but nobody knows that even tapping solar energy may be harmful in terms of the environment. What I am saying is a very subtle thing, because Earth needs sun rays for her metabolism, for her, the synergy with the existence, with the cosmos, to give us crops, to give us weather, the rain, and water, the proper temperature, the flow of air. All this needs a certain balance with the planets around. Sun is the star which forms the family of planet, moon and earth. So nobody knows, if we tap the whole energy on the earth's surface, it may be harmful to its ecology, to its environment. Nobody knows. People say that we can generate so much of energy from solar, but tapping more and more and not allowing the rays to go to the earth may also may have negative effect. So honestly speaking, nothing is like green energy. What I'm saying is, whether wind, whether solar or anything. So whenever we tap energy from the source, we always disturb the nature. It is only the matter of how much we disturb. It's like a stability study. If the oscillations are within limits, it will come to its stable point. If the oscillations are larger, then system go in an unstable condition. Same thing is true, maybe true for nature. If we disturb it within limits for our survival or for our excellence, then perhaps nature will settle to its equivalence, to its rest. But if we disturb too much, whether it is a coal, whether it is a wind, whether it is a sun, I think consequences will be there in long term. This is the potential for the wind power density. You can see the red color shows, maroon color shows the high wind density basically, and the light blue color shows the less wind density. So those are hot areas where the solar is very strong, and those places the wind will be very less. Near the sea area, you can see here, this is like this belt, you see this belt, there is more wind energy. In India, if you look our southern part and the Western Ghat, you can say Gujarat side or the Andhra Pradesh, Tamil Nadu, there are more scope for the wind generations. While in Rajasthan, Jammu Kashmir, there is more scope for the solar generations. Okay, so here this slide represents what is the scope and where is the focus in terms of the energy generation. So we can see here that the solar development progress is 51% over the 10 years, this 2014 data, 2004 data. So over these 10 years, you can see the growth rate is 51% for solar, and the growth rate for wind energy system is 23%. So although they do not contribute much in terms of the total production of the electricity, but their rate of growth is quite high. Okay, and solar has the highest growth rate, and the potential for solar is expected to be very high, and the growth rate also is projected very high. So in the coming time, these two technology, the wind technology and the solar technology, will be more expanding and evolving in terms of the non-conventional energy generation. There are others also, like if you see the geothermal is 4% and biomass is 9%. So although biomass have more generation, if you see the previous slide, but the rate of growth is very less. The overall growth rate is 5%, not really much over 10 years, but in this the solar and wind have more contribution. Now coming to India, as I said, the India's total installed power capacity is 326, now close to maybe 360 gigawatt capacity. Out of this, 218.32 is the conventional, which is based on the fossil fuel, and 108.52 gigawatt, which is 33.21, is the based on the non-conventional. It is very interesting to note that our non-conventional energy generation is more than the world average. The world average is close to 25%, and our generation is 33.21%. Because maybe the urban, the rural side, this trend of this using the heat energy, solar panels, the solar tube bells had started, and this has have a drastic effect on the contribution of the non-conventional energy part. Now, out of this 108.52, okay, the total installed capacity, total renewable generation capacity is 57.26. Out of that 108, the 57.26 is the purely renewable energy resources. Now coming back here, just one this side, you can see this graph actually. So 192.16 is coal out of the total fossil fuel, and 25.3 giga is gas, and 0.8 is generator. Okay, and this total forms around 218. If you add this together, okay, this will be 218, this one. And here if you add renewables is 57, as I said here, okay, correct. So renewables and plus the hydro makes 108.52. All right. Normally people won't include hydro in renewables because hydro have been earlier, long time back, and they call it green, but it is considered almost a conventional way of generating the electricity. So this forms 44.4 and nuclear 6.78 giga and renewables 57.26. The total makes 108.52. Alright, clear? This is India's scenario. And looking at that, we go into more details of the renewable energy generation in India. If you look the sub-parts of the renewable energy generation, then we will see that out of that 50, how much? 50.26, the 32.28 comes from the wind. You can see the blue region. Okay, this comes from the wind, and this forms 56.3%. Solar forms 12.5%. Small hydro is considered the perfect renewable energy source. A big hydro is not part of the renewables, although it is a green energy source. Biomass is 8.13 and wind to base to power is 0.14. This total forms the wind, solar, small hydro, biomass, base to power. The total forms 57.26 gigawatt. Okay, and if you look in terms of the rank in the world, then we are fourth in the wind generation, 32.28 gigawatt. We are seventh in the solar generations, 12.50 gigawatt. Small hydro 4.3, biomass 8.1, and base to power is 0.114. Now going into more details, what is the scope, the evolve and to expand in particularly the wind and hydro and the solar. So it is expected that we can grow about 102 gigawatt from 30 gigawatts, 38 gigawatts. So we can go almost 3 times what we have now, and this is very good number actually. 102 is almost 1/3 of our total generation capacity right now. Hydro can go up to 20 gigawatt, bioenergy can go 25 gigawatt, and solar can go at 750 gigawatt. So the solar potential is expected almost 60 times of the current solar capacity. 60 times. So in the current situation, the solar is being viewed as the most potential source in the future to be developed and to be expanded, to be evolved. And this is possible with the very fine application of power electronics to power system, having suitable converters, the inverters, interface between the distributed energy resources, DERs, and the grid and the local load and the storage. So it's a lot of work over power electronics, power system, control, and the DSPs, that is these signal processing techniques, to interface, to control, to coordinate all these entities in the power system. Now what is the target as far as your country is concerned? The government is planning to at least target 175 gigawatt by year 2022. Quite ambitious as usual. India is quite ambitious, although nothing moves with a fast rate as they plan it, but okay, nothing harm to having a very ambitious figure. So wind is is expected to expand up to 60 gigawatt by 2022, small hydro 5 gigawatt, bioenergy 10 gigawatt, and solar they expected to expand around 100 gigawatt. And the renewable energy capacity is 33.8 gigawatt, which increased to 46.33 gigawatt 2016. So the increase rate is around 40%, 35.98%. Okay, and we set target to achieve 40% from 17.51% based on the non-fossil fuel, that is the non-conventional energy sources. This report is from the Ministry of New Renewable Energy, December 2016. Now let us come to the research aspect and our study aspect. That what are the challenging points when we interface these energy sources, particularly non-conventional energy sources. Okay, so these are three important parameters: variability, uncertainty, and non-synchronous generation. Variability means that all the RES means the renewable energy sources, they are not continuous in nature. Alright, when the weather changes, they changes. For example, the solar production depends upon the sun, the weather at particular location, okay, the rainy season, and the cloudy nature of the atmosphere, and so on and so on. So there are many conditions on which that depends, and that is almost for all the non-conventional energy sources. For example, wind. So variability is very high, and therefore variability also is kind of a uncertainty. You may know for 7 days sun may not appear in winter days, or for 7 days wind may not come. So it will be totally off. The storage may play a significant role in these two conditions of variability and uncertainty. And then non-synchronous nature. Mostly the RES do not belong to the synchronous nature. Now what is synchronous nature? Like synchronous generator, it is tuned with one frequency in the network, but these are not of the nature of the synchronous generation. Okay, mostly DC and AC will be coming from this output, but its nature will not be synchronous. So what are the things that can be done? It's basically to have a better storage energy reserves which can fill the gap of the variability and uncertainty, and a capacity which is needed to provide the frequency response, that is to emulate the synchronous nature in the distributed generation resources itself. So these are the challenges, and these leave the scope for work technologically in terms of the development of devices which can fill this gap. And in this course we will try to study these entities of the microgrid as well as of the grid system, their behavior, how these can be addressed with the help of the storage, the generation, and the load and the grid combinations. Just let us overview, then we switch over to our main thing. So this is the overview. I think I have covered this. This is the same thing as I have done earlier. So you can skip this slide. And the target we have discussed, but something more is given here. This is expansion of that, maybe much years ahead, like 20 gigawatt of solar power have been achieved in the last 4 years. Okay, and 4 of the top 7 largest solar plants, as I discussed about this. And we have a solar plant about 2,255 megawatt in Rajasthan. India has the largest 100 gigawatt of solar power plant by 2022. So So this is state-wise generation for the solar plant capacity. And this shows about the wind and solar potential in India. I have talked about the world, this is about India. So you can see it here that those maroon color shows the wind potential this side, and here the red maroon color shows the solar potential. Okay, so this region is more, solar potential, having more potential for the solar here. All right, so I hope you got a good overview of the world as well as other countries and our country India. And I think you have a good guess and good feeling that where do we stand, where we need to work. Now I will switch over to microgrid systems. Now with that whole overview, let us try to connect to ourselves the microgrid structure. So when I say microgrid, basically it means that it has many components. Okay, the one component is the existing AC grid. This is the existing AC grid. And the other components are the DC grid formed to take care of the DERs. What are DERs? Or RES, renewable energy sources or distributed energy sources. The meaning is same. And these consist of maybe solar or fuel cell or wind turbine. Broadly speaking, these sources can be categorized into two forms. Number one, either the output is AC or DC. That's all. Any non-conventional energy sources can be broadly categorized into AC or DC type. Clear? So when I say DC type, the output is DC. When I say AC type, the output is AC. And the clear examples are solar plant is DC type and wind turbine is AC type normally. PMSG creates DC, but then AC is converted into DC. Therefore, to form the DC grid, we need to have the conversion from DC to DC for solars and for wind turbine AC to DC. So we use these DC to DC and DC to AC and AC to DC converters to form the DC grid. DC grid is here. As the DC grid may also have electrical vehicles, we may have the hybrid energy source storage systems, HESS. HESS stands for hybrid energy storage systems. AC loads through DC and AC converters, micro turbines through AC and DC to AC. So you see, on the grid side we have a micro generator, maybe diesel generator, then we may have a AC utility power system itself, and we have a wind turbine also direct through AC grid. This is a integrated, microgrid system. It has all kind of configurations. In future, this will be the nature of power system. Okay, where we combine AC and DC. How much time we have left? 5 minutes?
Yes, sir.
Yeah, if you know the future of the, the history of this electricity generation, it is a tremendous work of, thousands of people, scientists, engineers, more than that, who evolved our AC system. What we have today is a lot of work of human mind over almost, I can say, 500, less than, even more than that years. When Thales started, the philosopher Thales started with the concept of the electricity generation by simply rubbing the comb over your hair. And before that, Indian scientists, you can say, even those saints, the rishis, who said there is a minimum particle called, atom, they call it kernel at that time, okay, which has a capacity to mimic the whole universe in terms of its motions, and charge nothing but the current, nothing but the charge in motion. So it's not only one person. We know Nikola Tesla, we know Einstein, few of them, but there is a huge number of great minds who worked over a long period of time, who gave us so much that we stand today. and we take all things as a granted, but there's a lot of work behind that. Even to develop AC and DC, there will be huge bar between the scientists around 1880, if you look at the history of electricity generation. Actually, the first power plant was DC power plant, developed by Thomas Alva Edison after inventing a DC battery. But at the same time, there was development of the transformer, the AC generation single phase and double phase motor by Nikola Tesla and many more. Nikola Tesla is just front name. There are many people behind that who are working. And then comes the three-phase machinery, the compromise between the polyphase and between the two-phase, because two-phase machine was not self-starting. So they finally a lot of imagination was required to create three-phase systems. There is a long history for that. I will not go into that. But the idea is that there is a AC and DC now, and they work in very close intimation via the interface of power electronics. So power electronics is a beautiful and very emerging technology which removes the differences of AC and DC. We can easily transform, we can easily condition from AC to DC, DC to AC, and hence converters. So converters are very hearts of the microgrid system. Okay, whether it is an inverter, whether it is a rectifier, whether it is a DC to DC, whether it is any other converter, all makes a very much the central part of the microgrid system. Okay, so I will stop here and I will continue from the some more slides are there about the structure. I will discuss about them, and then in the next week we'll start from the first unit, so that you have a broad spectrum of understanding, and then we can switch over to our more focused units of this content. I will stop here and we will meet tomorrow by 9 o'clock.